we are going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about a few characterization techniques. So, potentials that can be used for characterize the nanomaterials, like any materials that we prepare by using a particular method. So, with the help of TGA, it is thermogravimetric analysis. With that differential thermal analysis also we can find out whether the materials is stability, means up to what temperature that material will be stability. The material property means whether it is exothermic, endothermic materials or heat generations or heat absorbs is there. So, when some material changes one particular phase to another phase, so with increasing temperature, so that we can easily find out. So, using this method, so these TGA methods means actually here you can see, means when we prepared any coke deposition, suppose carbon deposition, CNT depositions on a particular catalyst surface or nanomaterials that we have prepared for specific applications, particularly multi-wall carbon nanotube or fullerenes or single walls, whatever the materials that we have prepared. So, the nanomaterials, it is deposited over the surface of the catalyst. So, at specific times we have waited for the reactions from precursor to, means any gas precursor, let us say methane, that is decomposed over the surface of the catalyst, and then it's deposited carbon nanotubes over the surface of that material. So, the quantification is very important, means how much, means in terms of weights. Suppose if we are using 1 gram of catalyst, so after half an hour or 30 minutes, so how much quantity of the CNT are deposited over the surface of that materials, that easily you can find out using these TJ instruments or any experiments where coke is deposited, how much quantity of coke, phase changes of the materials or not. So, here this is the experimental setup. So, you can see TJ experiment. So, here's furnace is there. In this furnace there is a balance is there. In the balance one is sample holder, sample pans, another is reference pan is there, and in this particular furnace we can control the temperature from 25 to 1200 degrees centigrade. So, high temperature we can go, and initially we have to put a sample in a sample holders and reference pad we have to take, and then difference means both would remains inside of the furnace. Initially you can parts with the inert gas or maybe some oxygens, depending upon that experiments we can part the systems with the appropriate gas, and then we can heat up or increase the temperature. Here you can see that furnace is there. So, this is the furnace. So, if we increase the temperature of that system, so then materials also will be heated up as a result. If we pass oxygens or air, so then if carbon nanotube is deposited, that will be oxidized, CO2 formations would be there. So, that would be leaves as a result. The amount weight that is present in that materials initially, that will gradually decrease with increasing time. So, that we can get. So, that would help the quantifications of that materials. So, how much quantity of that materials is there, like that any other nanomaterials, porous materials we can synthesize, we can prepare, that can mean specific property if we want to know. So, with the help of this TG analysis we can get. So, here is the applications. You can see that porous materials or catalyst or nanomaterials, whatever we are preparing. So, we can using this particular TG analysis, oxidative stability of that materials, lifetimes of that products, or used to measures the residual solvents or moisture that is present inside of that materials or pores, how much quantity of that solvents or volatile materials are present in that materials, that we can quantify. Also material property, the materials sublimations behaviors, at what temperature it is sublimed, so that we can find out. It is also study the kinetics of reactions rate, constant activation energy for specific means reactions, that we can find out using this analysis. So, it is the temperature range I said 25 to 1200 degrees centigrade, microbalance is used. It is actually mass change or enthalpy changes, that is actually when we heating up that materials that is taken in that pans or sample holders and heating up, the mass change will be there, at the same time enthalpy changes would be there. So, if mass changes is there, so percentage weight loss, initially it was 100%. So, mass what the quantity, and with increasing temperatures the mass loss gradually decrease. So, mass loss would be there. So, percentage weight loss we can find out. Okay, so here's DT analysis is also there with the TG analysis. So enthalpy change and phase change of the materials that can be measured easily. Suppose we have samples and reference material samples is heated, both would be heated up. So if there is any temperature difference in between samples and reference materials, that we can monitor, we can record it, that in thermocouples would be there placed in both the pans, and very small temperature changes are there, or maybe weight changes are there, so that we can find out, okay, enthalpy change or phase change is there or not. So we can find out if suppose a material is exothermic, any material that may be exothermic or endothermic in nature. So if it is exothermic in nature, so delta would be negative and delta would be positive. So here temperature changes along delta T, reference temperatures, and the material temperature or sample temperature. So that is the difference. So this is the temperature changes. So if initially there is no changes, and after that maybe either it is drop, and then at this particular temperature it would be dropped. So then we can say that material is endothermic, means temperature gaining from source or supply heating, supply heat, from that it is gaining heat. Or if this way it is going, so means if it is increase, delta T increase, then the materials would be exothermics, either endothermics or materials would be exothermic. So temperatures and temperature changes, if we increase the temperatures, so delta T, if it is behave like this, then it is endothermics, and if it is behave like this, it is materials, we can say it is exothermics. Similarly, in case of the enthalpy change, here delta T changes, similarly delta H changes also we can find out with increasing temperatures. So either it is positive or negative. So based on that we can say either the materials is exothermic materials or endothermic that is behaving. So depending upon that, so we can change our system. So by that way, that is the use actually, so that we can analyze the material property that we have synthesized. Okay, so now is the Zeta potential, that is actually when we materials prepare, that is the nanomaterials. So there are many methods are there. So means solvothermal methods, solvents, means precipitations, many methods are there. Top downs, bottom up approach, many approach methods are there. Chemicals methods are there, where the Zeta potentials is very important. So means when a solutions we have taken a precursors, and then we can change that pH of that mediums, or we can use different surfactants, many way we can change. So then sometimes we need a stable solutions where nanoparticles will be distributed in that particular solvents to increase the thermal property or any other property of that materials, mass transfer property, heat transfer property, means thermal conductivity. If many things we can use that nanoparticles for with any particular or specific solvent. So then and also preparations of the nanomaterials from solvent precipitations or some way. So there's this Zeta potential is very important. So actually it is a measure of electric charge on the surface of particles. If we prepare a particle on the surface of that materials or the nanoparticles, some charges may be developed, either it is positive charge or maybe negative charges would be developed, that is surrounded by that materials of that nanoparticles. So when it is, let's say it is suspended in any solvents, and depending upon that, so that stability of that nanoparticles in that solvents will be, if it is maybe highly charged or maybe low charged, or if we also the charges that is surrounded by that materials also we can change by different factors, maybe additions of acid, base, or any polymeric solvents, surfactants that we can use. So by that way we can change this surface charges, electric charges that would be developed on that particular material. So here depending upon the nature of, here few example I am showing. So here suppose these materials, there are some functional groups are present, so that is acidic groups. So when it is ionized in any solvents, so then negative charge that would be developed on the surface of that materials. Okay, so then we can say that the materials is negatively charged outside the surface. Sometimes if it is materials is like this, and if it put that materials in any solvents, then there would be ionizations, this hydroxyl group would be leave to the solvents, and then some positive charge will be developed on the surface of that materials, either it is positive charge would be developed or negative charges will be developed. So depending upon that, we can categorize that materials whether it is positively charged surface or negatively charged surface. Sometimes surfactants also we can use. There are different type of surfactants, I said cationic surfactants or anionic surfactants that we can use, that would be also attached to the surface of the materials, and depending upon that also the changes of natures of surface will change. At the same time, pH also at which surface charge, and sometimes this addition of acid or base in that particular solvents, we can change the pH of the mediums, as a result positive pH or negative pH, and sometimes neutral pH also. When there is neutral pH means there is no charges on that materials or surfaces, hence that materials will be means neutrals we can say. So as a result there will be depositions or coagulations of that materials. So now the zeta potentials, so how we can express, actually it is the electrostatic means potentials at the sleeping planes of nanoparticles that is dispersed in a medium. So I said nanoparticles, we can say here's the nanoparticles that was taken so in a solvents. So this is the solvents. So here these are the nanoparticles that is uniformly distributed. Okay. So that nanoparticles is distributed. So some electrical potential, I said, that would be developed means with that solid particles, and this is the liquids. So in between them there is some interface. So in that interface some electrostatic potentials will be developed. So that is actually we say it is a zeta potential. So that is expressed in terms of these symbols, that is Greek symbols zeta. So that actually measures means the potentials or that electrostatic potential that is developed outer surface of that particles, that actually indicate the degree of repulsions or attractions between the adjacent similar charged particles present. This is particles, another particles are present. So it's that is charge means similar charges is developed in that particle outside, and apart from that so there is another charges are also there. So one layer is there, so diffuse layers, loosely bound layers, imaginary layers is there. So this is particles and outside positively charged developed. Okay. So apart from that, so in this particular surface or locations, so that potentials or electrostatic potential that would be developed, that is actually zeta potential. So it is sometimes actually I said that nanomaterials whatever we have prepared, sometimes it is initially it was bulk size and then size reductions we are doing means increasing the surface area, as a result surface to volume ratio increasing. So once nanomaterial changes from bulks to smaller, surface to volume ratio increase, therefore surface charges that is present outside of that materials, that actually play sometimes crucial roles or critical role for that stability of that materials in that particular solvents. Means when you have taken that materials in a particular solvents and that is distributed, so the material stability, aggregations behaviors, dispersions and functional performance, everything that depends on that particular zeta potential or charges developed on that materials. Okay. So therefore means actually this zeta potentials expressed in terms of millivolts. So this is actually quantitative value, and to describe how strongly the particles repel or attract each other so when they are placed in any solvent or medium where they are placed. Okay. So here's the particles means here the particle that is suspended in any particular solution that is surrounded by I said some ions. So this is positive ions. So and then this layer actually is called actually tightly bound layers, that is counter ion that is directly adsorbs on the surface of the particles, that is called Stern layer. Okay, Stern layers. So this is means in this is particles. So in the outer surface of the particles some positively or negatively whatever, so that is layer formation, that is Stern layers, and after that actually these layers you can say apart from that, so that is called diffuse layers, a more loosely associated layer of different ions that is present within that layers. Okay, of that particles. Okay. So here's actually that ions can move, so when particles will move with that ions also will move from in one particular point to the another particular point. So when that particle is moving, so with that the ions is also moving. So okay, so here the potentials will develop. So after that a small distance, so you can say this distance a diffuse layers is there. So here the potentials or charge develops in that particle. So that is actually zeta potential. So from particle surface to the distance if you go, then the zeta potentials that would be developed. So that in that diffuse layers that would be gradually decreased. So here you can see the distance, so it would be like this. So zeta potential at the surface that would be very strong, and after that with increasing distance from the surface to that mediums, then that it gradually decreased. Okay, so here it is means just diagrams you can see. This is the Stern layers and this is the particles actually that is developed the charges, and this is the actually diffuse layer. This part actually this is diffuse layers. Okay, so why zeta potentials actually important? So it actually indicate the stability of that nanoparticles or nanomaterials that we have developed, that is present in any colloidal solutions where that colloidal that particles dispersed in that particular solution. Sometimes we need to prepare a stable colloidal solutions where nanoparticle specific nanomaterials would be present. So that stability of that materials is very important. So okay, that stability of that material. So I said that sometimes we use different type of thermal fluids for a specific heat transfer, mass transfer applications. So there to improve the thermal conductivity, heat transfer rate if you want to increase, sometimes with that particular specific solvent some nanomaterials also we use to increase the thermal conductivity of that solvents. Okay. So if that solvents nanomaterials is properly dispersed about that solvent, so then the property of that solvent remain unaffected. If it is not properly dispersed and that nanomaterials is coagulated and large particles formations is there and deposited, then the property would be changed or that would be affected with the times. So actually with the times that zeta potentials of that solvents we have prepared with the help of nanomaterials. So if we measure and see after a long period of times that zeta potential of that solvents remain constant, then we can say that this is the stable solvent that we have prepared, and after that period of times remain the same. So high zeta potentials, either it positive or negatives whatever, so that is high. So it indicate actually strong repulsion between particles, so that particles remains in that solvents. So if it is either positive or negative whatever, so if it is high zeta potential, then that actually indicate a stable solutions is there. If zeta potential is low, insufficient repulsive force in between particles is there, as a result particles will be aggregate. So once particles will be aggregate in terms of floculations or coagulations, so means particles will be deposited, so then particle property means therefore the solvent property will affected. Okay. It also indicates aggregations behaviors I said. So if zeta potential is close to 0, so either positive or negative is good, and if it is close to 0, then aggregation should be there, and suspensions means remains dispersed and stable, high positive or negative value. So negative or positive value, that is zeta potential, that is good, and if zeta potential is equal to 0, then it is aggregate or particle aggregations or stability will be affected. Okay. It also guide us for formulations of actually from applications point of view. So I said there are many industry, pharmaceuticals, cosmetic, paint industry, they prepared that highly viscous solvent. So that actually once we measure the zeta potentials of that particular paints or cosmetic whatever, so then that actually helps us. So that's materials whatever we have prepared, that is a stable means the means different component compositions that was components added to that to prepare that paints or cosmetic whatever that material. So that gives a stable means liquid whatever that we want to prepare. Okay. Surface modification analysis also monitors how means modify the particle surface by using suppose initially the zeta potential of that particular solvents in terms of negatives or positives, we have that specific value at the beginning. So with times that zeta potentials may be changes. So means coagulations or flocculations is there, or precipitation sedimentations is there. So that also we can change by additions of different surfactants or specific acid or base we can add by change that surface we can modify. So here you can see that means on the basis of the zeta potentials how we can assess whether the solvent is good or not. So since different nanoparticles are present in solvents, we make a solutions, then the solutions we have gates and we can find the zeta potentials value. Zeta potentials 0 to 5, then flocculations or coagulations possibility is there, 0 to 30 either in terms of plus or minus whatever, both are equal. So incipient instability that indicate 30 to 40 moderate stability, and 40 to 60 good stability, and if greater than that 60 either it's plus or minus, so excellent stability. So this is the zero lines, so either positive lines or negative. So zeta potentials in this way, this is extremely stable, excellent stable. So and in between that is very less stable. We have nanoparticles in particular solvents, we are getting some solvent solutions. So the solutions whatever we have, so we can measure the zeta potential of that particular solvent. So if the zeta potential is 0 to 5, that indicate flocculations of coagulations of that particular solvent, that is not very stable, very less stable solutions that we have. So if it is 10 to 30 incipient instability, 30 to 40 indicate moderate stability, and 40 to 60 indicate good stability. Or if the zeta potentials value either it is positive or negative, so if it is x more than that or greater than that, so then it is the solutions which indicate excellent stable or stability. So here you can see the zeta potentials value, so that is in terms of millivolts. So if it is 0, then I said flocculations, coagulation, unstable solutions that we have, and if it is either positive or negative, so that much value, so then it would be excellent stable solutions that we have prepared. So next measurement of zeta potential. So zeta potentials how we can measure experimentally. So it is based on electrophoresis, so where charged particles migrates under an applied electric field. So suppose you have a solutions you have taken and there's two electrodes are present, and if we develop some electric fields in that colored suspension solutions, so then what would happen, charged particles will move from the oppositely charged electrodes. So suppose that solvents or solutions we have positively charged particles, so that positively charged particles that present in that solutions, and so once some applied field should be developed, so then positive charge will move towards cathodes or negative electrodes. Okay, so this rate of movements, so we can measure experimentally. So competing factors means here, so when that movements of that particles either it is positively or negatively charged particles that is present in that particular solvents, so that depends electric force that pulls the particles from a particular locations to that particular electrodes. Also viscous drags, so that is would be opposite directions. So fluid resistance force, that would be opposite direction. So here when electric field that was applied, that attracts the particles towards these directions and in opposite directions, so viscous drags would be there. So there would be after a certain period of times there would be an equilibrium, so particles quickly reached a constant speed when these forces would be balanced, means one electric force and viscous drags both would be balanced, equilibrium will reach. So then at constant speed particles will move from one point to the another points. Okay. So here's high electrophoretic velocity of that particles when electric field is developed. If that movements or velocity of that particles, charged particles from one point to the another points, the rate of movements, if electrophoretic velocity of that particles is very high, it indicate high surface charge, that means higher zeta potential. So rate of the movements from of that particles by applying electric fields, if it is very high, then having high zeta potentials. If it is low, then it is low zeta potentials, that indicate actually. Okay. So electrophoretic mobility or that particles movements, so that is particle velocity when charged electric field is developed. So per unit electric field, so particle velocity per unit electric field strength. So actually electrophoretic mobility or the movements of the particles in that colloid solutions, that actually define the electrophoretic mobility. So this electrophoretic mobility of that particles, that depends on that electric field strength that we have applied, and dielectric constants of the mediums, viscosity of the mediums. These are the various factors that would affect overall potentials of that particles movements, okay, or electrophoric mobility of that particles, that is zeta potential. So electric fields, if it is higher fields, then faster movement should be there. If dielectric constant of the mediums is higher dielectric constant, then stronger electric force that indicates, and viscosity is high, then more resistance will be developed by that mediums that we have, and higher zeta potentials means faster movements. When particles will move very fast, it indicate higher zeta potential of that. So, okay, so here electrophoretic depositions means, so when zeta potentials we are measuring, so electrophoretic depositions is very important. So when applied electric fields were applied, so charged particles is present in that solutions, suspended solutions. So here it is distributed. Hence we applied charged particles, electric fields. This is electric fields were applied, and this is charged particles that is suspended. Colloid solutions formations is there. So electrical chargings, this is dispersions, and then when applied fields we have applied, then it would move towards anodes, and then it would be deposited over the surface of that electrodes. Okay. So this is actually depending upon electrophoretic deposition. So it depends, this electrophoretic deposition, that depends on that liquid means charged particles and movements and zeta potentials of that particles is present. Okay. So here in this case the solvents or liquids that remains stationary, but the solid particles only that will move. So when electrostatic force will be applied in that mediums. Okay. So here's the zeta potentials actually experimentally how we can measure. So here's Henry's equations is there. So Henry's equation is this. So these equations you can use. So where UE is that electrophoretic mobility or measurements that we can get from experimentally. So experimental details I will discuss, and this is the dielectric constants of the medium. This is the zeta potential that we have to find out, and it is the viscosity of the mediums. I said that these are the factors, so that mobility will change, and this is the Henry's function that depends on the particle size and ionic strength of that mediums that we have used. So that depends on that solvents we have used. So here's depending upon different conditions, whether it is aqueous and moderate salt or non-aqueous. So double layer that will be developed, so thin layers, then particle size would be large, and then Henry's functions value 1.5. Depending upon this aqueous and thin layers, large particle size, Henry's functions usually constants this value 1.5. If it is non-aqueous mediums and thick layers, formation is there, that is particle size less than 100 nanometers. So then these Henry's functions we can consider equals to 1. Okay. So depending upon that, if we put these Henry's functions this or 1.5 or 1 depending upon the mediums we have used. So if it is water based solvents, so then this, and if it is non-aqueous oils or others, so then it can put 1. Okay. So then these Henry's equations, this was the Henry's equation that would be changes into this or this. Okay. So depending upon that mediums, either this or this equations we can use, and zeta potentials we can find. So once we know that electrophoretic mobility and viscosity of the medium and these dielectric constants of the mediums, these are the components. If you know, then zeta potentials experimentally we can find out. Okay. So these zeta potentials affect various factors. So that is one of that is the pH of the mediums I said. So when pH we can control either 0 to negatives or 0 to positives. So suppose a solutions having pH close to this, so if we add some acids, so then pH would be moved to the lower pH, so then zeta potentials will increase, or maybe suppose pH is up to this, if we add some basic components, so then pH will move towards this. So then the zeta potentials also either will move these directions or these directions by additions or controlling the pH of the mediums. So when pH equals to 0, then there is means depositions of that material should be there. Okay, so depending upon alkaline conditions or acidic conditions, those surface we can charges we can increase means positive charge or negative charge. That way we can means if we acidic conditions surface are more positively charged, if as surfaces are acidic conditions the particles will be more negatively charged. So depending upon that, so at means by controlling pH either in using acid or base, we can control the zeta potentials of that materials that we have. Okay, so now there are some other ionic strength and conductivity that also will affect with the once zeta potentials it changes, specific ion adsorptions also, and concentration of formulations. Sometimes we use some surfactants, polymers or other materials or additives to that also sometimes covered or sealed the charges. As a result, the overall zeta potentials would be affected or that would be changes. Okay. So here experimental setups is there, so you can see. So here the experimental setup, so that is consist of a laser source and electrophoresis cells is there, and their optical detection systems is there, and software is there. So we can using these setups a particular solvents we have charged or nanoparticles present that is suspended in there distributed, so that solvents zeta potentials experimentally we can find out. So actually the laser source actually helps, that is beam is used to illuminate the particles that is present in solutions. Okay. So electrophoresis cells, that is a transparent cells of two electrodes, and electric field when it is applied, then particles will move from one particular point to the another particular points, and that movements we can measures by Doppler shift in scattered light, that once particles will move, so and light will be fall over there, and then Doppler shifts of scattered lights that would be collected in a detectors, and so with the help of that detectors and that optical lights, that movements we can find out and zeta potential of that solvents we can find out. So different now means what is called zeta potentials and what are the various factors, and experimentally how we can find out that zeta potential of any solvents where nanoparticle is present. So different factors we have discussed. So now one two examples we will give. So where let's say here's alumina titania that solutions was taken. So if we vary the pH, the zeta potentials also will vary. Zeta potentials is in y axis. So the zeta potentials you can see for a specific concentrations. So zeta potentials initially it was at low pH was high. If we increase the pH, zeta potential which go neutrals, and then further if we increase the pH, the zeta potentials will increase negative value. Okay, so the zeta potential is positive at low pH, and with increasing pH then it becomes negative at high pH. Okay, so similarly for others materials also the zeta potentials also change, and this point where zeta potential zeta is called isoelectric point, so that particular points neutrals. So okay, similarly some other potential also influence particle concentrations also, that is very important, that is present in solutions. So if we increase the concentration of that particles in that solution, so then zeta potentials also will vary. So here you can see the zeta potentials initially it was like this, negative value extremely high for low concentrated solution. If we increase the concentration of the solutions, the zeta potential going to 0, and then further it would increase when concentrations of that particles concentration increase. So either it is negative or positive whatever, so that also will change. If we concentration of that particle in that solutions, that zeta potentials also will vary. In some cases it is affected abruptly, and in some cases it is not significant changes is present. So similarly other very examples are there. So with time also zeta potentials will change. So a graphite oils, graphite based oils was taken, so zeta potentials that was measured means 0.58% of graphite was used in a particular oil, so means 0.05%. So and zeta potentials after 0.5 hours it was measured this, and after 1 hours, so then it was decrease. So means that indicate actually that stability of that particles, nanoparticles in that particular oils. So with increasing times the zeta potential decrease, means stability of that particles in that particular oils, graphites, that changes. Okay, so different examples are here. Okay, so different factors are there. So zeta potentials, that is very useful characterizations, means for particularly colloids nanoparticles. So in that case we use this particular technique, so that is very useful. So today we have studied the TG analysis and zeta potentials for nanoparticles characterizations. So that is very useful techniques. So thank you. So today is up to this. Okay.